All right, we're back again. Next problem we're going to do is problem 15 here. And it says, find the moment of inertia about the z-axis of the solid cylinder x squared plus y squared less than or equal to a squared, 0, z between 0 and h. So this boundary here, our region, is a cylinder. So we'll naturally use cylindrical coordinates. Now, I wrote here the moment of inertia about the z-axis. Over here, let me move them a little bit, if I can, without moving everything. I guess I can't. But over here, we have the moments of inertia about the x and y axis. Okay? Notice that with the z, it has x squared plus y squared. With the x, it has y squared plus z squared. And with the y, it has x squared plus z squared. Okay, we don't need these now, but you have them in case you do. So, I sub z is, well, the integral, we'll talk about that integral in a second, of x squared plus y squared. dv, remember in cylindrical coordinates, the dv has an r dr, dz d theta. So r goes from 0 to a. Okay, that's this part of the, let me draw it. Okay, I can draw, here I've actually drawn the cylinder, but I actually like drawing these things in 2 dimensions. So let me draw a 2-dimensional version of this thing. And what I mean by that is here's r, here's z. Okay, so r goes from 0 to a, and then you just have this thing, but you really have it rotated around the z-axis. Okay, so that's what's going to give you the cylinder. Okay, all right, let's do another one. Use cylindrical coordinates to evaluate this integral, x squared dv, where E is the solid within x squared plus y squared equals 9, above the plane z equals 0, and below the cone z squared equals 25x squared plus 25y squared. Now, here's my attempt to draw the 3-dimensional thing. As you can see, I'm not good at that. Okay, but what I want you to do, notice the symmetry of the boundary. I should have said boundary curves in x and y. Here, if I replace x and y, it's the same thing, right? Same thing here. Okay, the only place that breaks symmetry is in the thing we want to integrate, but that's not really important for us right now. I mean, it is, but I'm wanting you to notice the symmetry in these two things between x and y. Okay? So what I'm noticing, or what I'm trying to say is, I really have this thing. Okay? I have this thing, and I have it rotated about the z-axis. Okay? That's what I tried to draw there, but I can't. But there, it actually looks better to me. So, let's do this integral. Integral in theta goes from 0 to 2 pi. That's going around like so. R goes from 0 to 3. That, if you think about it, is that x squared plus y squared equals 9 as the outer boundary. Okay. Z goes from 0. That's supposed to be 5r. Let me write that a little better. Okay. Now, in cylindrical coordinates, remember, x equals r cosine theta. Okay, so since x equals r cosine theta, okay, so our x squared equals r cosine theta squared. dv is r dz dr d theta. Okay, and then this is a pretty standard integral. I'll let you guys work through that integral on your own. All right, see you in the next video.